Good morning, students. How are you?
Good morning.
Good morning.
Okay. Good morning. So let's start today's session. If you have any doubts from the previous classes, please tell me. Okay. Paulette, please.
I have a doubt, but not about the previous classes. I'm seeing the schedule, and I noticed that we have exam on Friday. We have all the day for doing this exam, this partial.
The time you want to know, the exact time of that?
Yeah.
Okay. I'm unaware of that exact time. Let me look into it. It's partial assignment. I think you have the whole day. Yeah.
Okay. Thank you.
Okay. Okay. Yeah. So if you have any doubts related to this, you can send me an email, or you can also talk to the coordinator of the course, and he will help you. All right. So if you find any difficulties on that day. Okay. So any other doubts? Yes, Ivan, please tell me.
We're gonna solve the activities of the last homework, or you're gonna upload the answers in Blackboard.
Sorry, your voice is little not clear. It's disconnecting. Can you please explain again, or you can chat and send me a message? I didn't hear properly.
Yeah. Okay. Of the last homework, I like to know if we are gonna see the solution, or you are going to upload in Blackboard the answers of the last homework.
I'm sorry, I didn't understand. The last homeworks, you said something about the last homeworks. What did you want to know about that? It was not clear.
If we are gonna see in class the solution of the last activity.
The solutions for the last homeworks, you mean?
Yes,
Can you send a message, because your voice is disconnecting? If any other of the, I mean, if some of you from any of other of you students understand this question, can you please tell me? For example, yeah, please tell me, Anna.
I think is if we are going to check the homework, the solution of the homework.
Okay, he wants to know what is the solution of those homeworks, right? Okay.
Yeah, I also have some doubts in those exercises.
Okay. Sure, we can meet after the class, and we can try to solve the doubts, and we can try to understand. We can solve your questions. So maybe you can send me an email to meet one day. Let's program one day. We sit, we make a video conference, and we solve all these questions. All right? Is it good?
Okay, thank you. Fine for me.
Okay, very good. You're welcome. Okay, now let's start today's class. Any other questions If you have any other questions, please tell me. Okay. In the Blackboard, you are going to upload solutions for the homework. Yeah, now I understand Ivan's question. So he wants to know the solutions. Yeah, sure. I'll try to upload the solutions on Blackboard, or somehow I will try to communicate with you the correct solutions, right? Yeah, sure. Thank you. Okay. So now let's start today's topic. Today's topic is probability distributions. So we have to understand the concept of probability distribution. So by end of this class, you should get the idea what is probability distribution. And in the later on classes, we'll try to see how we can use them in solving our problems, how to in the decision-making process, right? Okay. So this is one of the important topics because here we introduce the probability in more mathematical way of approaching so that we can use it in solving our problems. Okay, so let's start with the random variables. What are the random variables? So how do we define? So we entered into a little bit of mathematics to understand what are the random variables, and then we try to get some understanding what is random variable. Okay, so can someone wants to give any information what is a random variable? So someone wants to tell me what is random variable, what do you think of it? Okay. Yes, please.
Maybe like a variable that doesn't have sequence or is aleatory or something like that.
Any variable is something we don't know. We use a variable, right? How is it different from a random variable? Let us see. Any variable from a data set. Any variable from data set. Any variable from data set. Data set is all of values. There is no variables. So variable from data set is something I don't understand, Jose. Okay, let me explain how I define random variables. So how do I define random variables, or in general we use is the random variables is we assign some values, some numerical values for the outcomes. For example, if you are flipping a coin, so if you flip a coin, so the output is heads or tails. So head and tails is something you can say like heads or tails, but if you want to mathematically use, you can use a random variable and you assign some number to it. So what do I mean? So let us say x is random variable for coin flipping. If I say this, x is random variable for coin flipping experiments. Once you what is the output? The x can be, x can be heads or x can be tails. But in mathematics, we don't use heads and tails, we use numbers. So what I say is x equals to 0 is heads, heads equals to 1 is. The question comes, why 0 and 1? So there is no reason for me to select 0 and 1. I can select any numbers. I can select 408. Here I will select 174. Any numbers. But for me, it makes more sense, or we can say more easy for me to use 0 and 1 because these are the smallest numbers. So I usually start with 0 and we take more numbers 0, 1, 2, 3 for all the possible outcomes. So random variable x gives, or it takes the outcome and we assign a number for the outcomes. For example, the outcomes for this experiment is heads or tails. For heads, I am assigning the variable, the value 0, and for tails, I am giving the value is 1. So I am defining it. And so for example, if I say probability of x, so how do we represent this? Probability of falling heads. Probability of x equals to 0. If I say this mathematically, what do I mean is means. And so what I'm saying is probability of falling heads. So this term for me it represents the probability, because I say P of what? Falling heads, because I'm saying x is equals to 0 is heads, x equals to 1 is tails, right? Let us say another example, like x is equals to 1, 2, 6 for each side of a dice. So if I want to know what's the probability that a dice is falling head, 1. So what I say, if x is random variable for a die showing experiment, then x equals to 1. With side 1, 2, with side 2, and it goes on until 6. So if I want to know what is the probability that a die shows 3 or less than 3, so how do you say? Probability of x less than equals to 3. When I say this, what am I asking is, my question is probability of a die showing a value 3 or less than 3. What is it? It can be, we know it is 0.5, but here we are not trying to solve the problem, we want to understand the mathematical notation. So we say probability of x less than or equals to 3. So let us give another example. Let us say x is a random variable, represents height of a student in a classroom. X is height of a student in a classroom. So I want to know what is the probability of a randomly selected student. If I select a student randomly from a classroom, what is the probability that his height is between 4 and 6 feet? So I say probability of height of a randomly selected student, his height is in between less than 4, 4 less than x less than 6. So what I'm saying is the probability of random variable is in between 4 and 6. So this is how we represent the random variables. The random variable alone is representing one of the outcomes. And if we don't have, for example, here height, in this height, we know height we measure in real numbers. So the x can take real numbers. Here it made me easy 2, 3, 4, 5, 6 because each side of a die it's having number of dots and we know the dots. So 1 dot represents 1, 2 represents 2 dots, and so on. For some cases we don't have anything like dots, nothing, so we just say heads are zeros, tails are ones. So this is how we represent the random variables. So there are two types of random variables. discrete and continuous. So let us understand the difference between discrete and continuous random variables, because we are going to use this in the future slides. So let's try to understand a little more about this discrete and continuous. So when I say discrete, I'm talking about some quantities which are available in discrete fashion. What do you mean by discrete? Which is available like chunks, like 1, 2, 3, and you can't get any value in between these two. For example, if I take the example of a coin flipping, it is having 0 and 1. You can't expect any other value other than 0 and 1. It's not possible. So here the variable or the random variable is discrete. Now let's go to the die experiment. In the die experiment, the outcomes are 1, 2, 3, 4, 5, or 6. So here again the values are discrete. So you can't get anything between 1 and 2 or 2 and 3, or there are no other numbers other than these 6 numbers. You put anything else, it is an invalid number, right? Okay, now let's go to the height. If the random variable is height, and let us say height of student in a class is x. So what is the height of any person? It is not a discrete, it is continuous. What do I mean by continuous number? For example, if you can take any number between 4 and 6. You can have 4.1, 4.11, 4.1111. You take any two numbers, there is always a number in between those two numbers. It means there are infinite numbers between 4 and 6. So what is the height of a student in a classroom? It's a continuous number. You can't just say this, you have heights 4, 5, and 6. No, you have 4, 4.1, 4.11. It's a continuous variable. You can just list out all the numbers because there are infinite numbers. But in other cases, you can list all the numbers, 0 and 1. Here 1, 2, 3, 4, 5, 6. Here you can't list. There are all the numbers between 4 and 6, right? So those are differences between discrete and continuous. So let me ask a question in a poll, and let us see if it is a discrete or continuous. Let me conduct a poll. Okay, the question is number of flights arriving at an airport on a random day is our random variable x. So my question is it a discrete or, is it discrete? You have to say yes or no. Okay, so it's a discrete, right? So all of you are saying it's discrete. So yeah, it makes sense because the number of flights arrive on one day, it can be 10, 20, 50, 100 or 110. So you always know it is some discrete number. You don't have 1.5. You don't have 2.6. You have some discrete numbers. Very correct. It's okay. Very nice. I'm stopping it. So now we understand what are the random variables, continuous and discrete. So let me share the screen again. Okay. So now let us see expected value. So we saw this kind of similar before, not similar, the same before, but let's kind of revisit this. The expected value in our context, in right now, we can say expected value is same as the mean, or we can also say average. So we all three are the same. So we try to find out how to calculate this. So we know how to calculate this, but we are going to do it again, and we do it with use of kind of probability. So before we did from the group data, now we do through probability. What do I mean? Let me show you. Let me open a new Excel sheet. Yeah, let me generate some random data. Let me generate some random data between 10 to, let me generate between 0 to minus 22, 20. Between minus 20 to 20. We always go positive side, so let me go a little bit on the negative side of the number scale and see how it looks. So I want to go generate, let us generate at 2000 data points. Generated some 2000 data points. Here is data. Let us group them. Let's group them from minus 20 to 10, sorry, minus 10. Okay. This is the lower limit. This is the upper limit. And the frequency, let me see the cumulative frequency first. The cumulative frequency, how do we get it? We get all the, let me see, how do we get it? Okay. With criteria, the criteria is less than. Okay. So I didn't like this. So let me generate some random data, but not 20 and minus 20. We'll see between 19 and minus 19. So random between minus 19 to 19. Why I did this, because I have to add extra column. I don't want to do that. Extra row. I don't want to do that. So let me do this way. I don't want to use this equal sign. Okay. This is a cumulative frequency. So what is the frequency here? Which is, the first one is the same. The second one is this one. So this is the frequency. So we know the frequency. We know how to calculate the relative frequency. The relative frequency is frequency divided by sum of all the elements. Here it is 2000. So let me say 2000. This is the relative frequency. So we already know this relative frequency is also the probability. So let me put this in this context, like the x is exactly the middle of these two. So plus let me explain again why do I say the relative frequency is the probability. So if I say, so what is the probability that you randomly select a number from this big data we have? The big data means that 2000 samples, meaning we have the 2000 population we have. If you select any one random number, what is the probability that it falls between -20 and -10? So -20 and -10. What's the probability? Which is 0.23, right? So what's the probability that it is between 10 and 20 is 0.45. Sorry, 0.48. So this is relative frequency, and also it is the probability. So this is the probability, right? So how do we calculate mean? Is we multiply the relative frequency. Let us say it is RF. We represent with RF here. So how do we see this? Is X multiplied with RF. X multiplies with RF. Where is X? X multiplied with RF. But you see the relative frequency is a probability, so we are multiplying with the probability. And sum of all this gives us the mean. So the mean is equals to sum of all of this. 5.2. 5.21 is the mean, right? So we already know how to calculate mean from the raw data using Excel's formula. Let us show this is a table, or you can say group of data. And let's say from the raw data. From the raw data, how are we calculating is mean, average of all these numbers gives us 0.12. So there is a big difference between these two. So why do we have a big difference? Is it because of some error we are doing, or is it because of the grouping? So we can find it out if you make the group a little smaller. I mean group bigger, but the interval a little smaller. What do I mean? So let's say group of data. So this table is group of data with big interval. Let us make another group of data. Big interval. Now let's take another group of data with smaller interval. So how do we take the smaller interval? The first two rows I'm copying here. Here if you see, I'm taking a step of 10. Instead of taking a step of 10, what am I going to do is take a step of 2. So here it's a step of 2. Maybe go until 20, right? So the table is a little bigger, but it will, I guess it's going to be a little more accurate. So let us see how it goes. But there is a problem with the frequency. The frequency I'm doing is okay. So I understand the problem is with the frequency. The frequency is some divided minus this one, right? Yeah. Yeah. So this is the correct answer, but still you see it's 0.5, but the actual answer is 0.12. So let us see if it improves a little. So this one minus this one gives the frequency. Okay, so this is the relative frequency. And now let us see the mean from the big interval. We got 0.5. From the small interval, we get sum of all this. It's getting worse. I don't know why. It should supposed to be increasing. I was expecting it to be better. So let us see taking a little bit more. Let us see the complete data. Instead of doing this, let us see x being the complete one. See minus 20 to 20 to take 1. So let us see the complete minus 20 to 20. And the cumulative frequency is, we just don't want cumulative frequency anymore. We can just go with the frequency, which is equals to count if range is equals to, or we don't have to say equals to, we can just say this is equals to this. Yeah, we have this, the relative frequency. And this sum is until here, right? So we are all to here. Yeah. Now you see the group data with smaller interval is exactly same as the full data. Okay. So the mean, if you have bigger data, bigger intervals, you get little incorrect. But if you have smaller intervals, you'll get more accurate answers. For example, here we are taking all the numbers, so we are getting exact answer. Okay. So what you have to observe here is I'm calculating the expected value or mean using the relative frequency, which is the probability. So why do I use the word probability? So when I say 19 here, it is 0.028, or you can say 2%. So if I randomly select any number from this big chunk in the population, so the probability that the number is minus 19 is 2.8%. So 2.8% of the times I get minus 19 as the answer. Yeah. Okay. So how do we represent the mean value? The mean we represent the mean. Here in our case, it is called expected value. Equals to, we can represent expected value of x. The expected value of x, or mu, or we can say x bar. So all these terms represents the mean. So what does mean says? What's the expected value? So the average value of the whole data, right? So how do we calculate? Using the probability of each number. So what's the probability of this number? Multiply with that number. Probability of getting minus 16, multiply with minus 16. So we multiply x times RF. RF is the relative frequency, or we can say it's a probability, right? Okay, that's how we calculate the expected value. Now let us see the next one is called variance. What is variance? Again, we saw this before. Let's calculate again. The variance is, so let me show the previous example how we calculated the variance. In our previous, the second session, we calculated the variance using this formula. Sigma square is equals to sum of frequency times x bar is the mean minus x squared, you see. But if you see Fi divided by n, we are talking about the relative frequency. So we multiply relative frequency with the squared term. So let's generate a squared term and then multiply with the relative frequency. What is the relative frequency here? The relative frequency, we are saying it's probability, right? Okay, so let us do that. So for calculating variance, we need x minus, we can say mean minus x. Remember, we told we can use mean minus x or x minus mean. It doesn't make any difference because when we do multiply with each other, it will always get positive. So it doesn't matter if you take x minus mean or mean minus x, it's the same. So what is mean? The mean we are getting is this value, right? Minus x. What is the x? X is minus 15. So this is the mean minus x. Now the question is, we have to do squaring of this. Mean minus x squared. How do we square? One way is to multiply the same number with itself. And we get some answers. You can get like this. Or there is another method. We just multiply this number. Oh, sorry. You can use the Excel's formula called power. This number, power we want the power to be 2, x to the power of 2. Here, mean minus x to the power of 2. This is, it's the same. So what is the variance? Is sum of all this, but we have to multiply with the relative frequency. So we have to copy this, multiply with the relative frequency. Relative frequency times this. So what's the relative frequency here? We know the relative frequency is here. This is the relative frequency times this number. Use this, right? This is the answer. The sum of all this. So let me put them in bold. Mean variance. So variance. So variance is sum of all these values. 122.6. So now let us see for the raw data what is the variance. We know variance, we can calculate. There are two types of variance, the population and sampling. We are taking the population one, so we take the population one. We need to for the whole and do this. It's 126.4. The answer we are getting is 122. So we see there is an error because of this grouping. So let us see with this another grouping. We think that this grouping is better than the previous one because we are having more detailed table, right? We are not missing any information. Ideally, it should show the same number as here. So let us see if it works. So for that, we have to use the same. So let me copy this. So the formulas will be copied down. So here we have the formulas. Let me copy. We have this. Then let me calculate this. Is sum of all these elements. We can see this value is very close to the raw data, right? Okay. So this is the variance. So how do we represent variance? We represent variance through the symbol sigma square. Variance is given by sigma square. This is the variance, right? Sorry, this is variance. So let's go to the next one called standard deviation. So once you know the variance, calculating standard deviation is very easy. Why? Let me first represent what is standard deviation, and then we'll see. Standard deviation is equals to the positive square root of the positive part of the square root is this one, so which is sigma. The positive part, because when you do square root, we can take positive or negative. So the standard deviation is positive number. Sigma is square root of sigma squared. So what do I get here? The standard deviation is square root of this number. And here we calculate standard deviation of the whole population, and I get 11.23, which is very close to the calculated one. It's little different, but it's very close. Yeah. So this is the standard deviation, right? Okay, now let's enter into the main topic called probability distribution functions. The probability distribution functions are which determine the relation how x is related to the probability. So we see some graphs from here on, and we understand what does these graphs mean. So we don't want to go in detail of all the probability distribution functions. Our objective is to understand what is probability distribution function. And at the end of the class, or the last topic we want to see, is the most important probability distribution function, which we want to see for rest of the course. For the rest of the course, we'll use that probability distribution function. So we should be spending more time on that, right? Okay, so let us see probability. There are three functions: probability mass function, probability density function, cumulative distribution function. So the probability mass function is associated with the discrete random variables, and the probability density function is associated with the continuous random variables. So what do I mean? So if you have a random variable x, if it is discrete, you can only apply, or you can say the probability mass function is applied to that. You can't use any other probability distribution function, right? Okay. So what's the probability mass function? We'll see what is probability mass function, but probability mass function is assigned only to the discrete variables, discrete random variables. And probability density function is associated only with the continuous random variables. And the cumulative distribution function is applicable to both the discrete and to the continuous random variables, right? So in the next slides, we'll see what is probability mass function, and we'll see why is it so different from density function, because the type of variable determines what type of function we are going to use. But both of them represents how the probability is distributed for all the outcomes you're expecting, right? So that's why I say probability distribution function. Okay. Let's go with the probability mass function. So what is probability mass function? Which is something all of us has already seen this, but we didn't put in this way of probability mass function. We saw it in terms of relative frequency. What do I mean? So in this way, we are saying the relative frequency is the probability, right? So let us try to take another example, and see. Once we solve the problem of, I'm not sure if you remember the reviews of the Squid Games. In the second session or first session, I remember that we took the Squid Games probability and we tried to calculate its mean. So now let us see the same information. This is a Squid Games reviews. So the reviews is this is the reviews, all the reviews of the Squid Games collected from IMBD. In this this review rating represents what is the rating, but here the rating looks like a date. You know why? Because it is. Can someone tell me why it looks like a date, not some number? If someone wants to say, you can tell me. Okay. It is because if we observe the raw data, it says the rating is 10 divided by 10 or 9 divided by 10. So when you use the 10 divided by 10, the Excel is interpreting as a date. 10 divided by 10 is thinking it's 10th of October, or 9 divided by 10 is thinking it's 9th of October. So, but we know it needs some processing to get the exact value. So 10 divided by 10 means the rating is 10. So 9 divided by 10 means the rating is 9, right? So here we have the rating. Okay. So now let us put the X. What does X mean? Now let's talk in terms of probability. So what is here is the rating, one of the outcomes. So if you have this lot of ratings, so let us say these are, how many people are there here? There are 1,185 people gave rating for the Squid Games. And then let us say we put all of them in a room and we randomly select one of them and we ask, what rating did you give? What is the probability that he says it is 1, it is 2, it is 3, it is 4, it is 5, or what we are going to calculate now? So let us put them 1, 2. We know the values start from 1, 2, and then until 10, right? So these are the X's. These are possible outcomes. Okay. So what is the frequency? Is the range is this one, the criteria is this one. Okay. So this is the frequency. Now the relative frequency. The relative frequency gives this one divided by sum of all of them. Okay. If I ask you a question, if you select a random person and ask what is the rating he has given, the probability that he says the rating is 3 is this one. This number indicates the probability that the rating given by that person is 3. What is the probability? It is 3%. Because it is 0.03 in percentage, you can say it is 3.3%. So this is called the probability mass function. So the mass, what do I mean? So how much weight does this rating has? This 10, for example, it's having 21.6%. So 21%, 21.6% of people said it is having a rating 10. So in other terms, in a room filled with all these persons who rated, if I select randomly one person, 21%, 21.6% of the times I get a person who gave the rating 10. Or if I select randomly one person, what's the probability that he gave the rating 10, which is 21.6. These all are the same. I'm trying to tell in different ways, right? Okay. So let us draw this graph. Let me draw this. Here I can draw in different ways, but I prefer using this. When it is discrete, I prefer using this diagram. I don't want to connect the dots because there is nothing in between 1 and 2. If there is nothing, I don't want to connect it. So I just want to put it like this. I select this. You say okay. So I get this graph. This graph says how many people give, or what is the probability that a randomly selected person give rating 1 is 0.05, and so on it goes, right? So what is probability mass function? Probability mass function is the probability of each outcome. It happens only in discrete. Okay, now let us see what is cumulative distribution function. Cumulative distribution function is, it is very similar to the cumulative frequency. It means, let us see the cumulative frequency, how it looks. Cumulative frequency is, let me put here the cumulative frequency. We had all the outcomes, all the people until then, right? It's like this. So what is the cumulative distribution function? Means we get cumulative frequency divided by the total population, which is here. Or another way of doing this is cumulative distribution function is adding all the probability mass function until that point. This one plus this one. So if I add this, also I get the same. These two are the same. Okay, so what am I doing anyway? So what am I doing is, or what as it says is, in mathematically what it says, for example, this number. What does this number represent? This number represents what is the probability that a randomly selected person has given a rating 5 or less than 5. So what is the probability? It is 19.7468, or we can say 19.7. So the probability is 19.7%. So let me ask you a question, like what is the probability that a randomly selected person has given a rating 3 or less? How much it is? So it is 11.39, right? So if I ask what is the probability that a randomly selected person has given a probability of a rating of 6 or less, I can say 0.28. Okay, now I ask you a question. You have to put a little bit effort into it and you have to tell me. The data is available here, the calculations are done. I'll post a question, a poll. You have to tell me. The question is, what is the probability of, stop sharing this, a randomly selected person has given rating 7 or above. Let me share the screen so that you can see what's happening here. You can use the information available here. Okay. The question is, a randomly selected person, what is the probability that he has given a rating 7 or above 7? Probability. So tell me, how can you calculate it? Should be giving rating 7 or above 7. Listen to the question again. The question is, what is the probability that a randomly selected person has a given a rating 7 or above 7, right? Okay. I got only a few people. I'm waiting for your answers. Okay, so let me stop this. So we have around, we have 8 answers in that. 3 says 0.4, one person says 0.7, one person says 0.1. Okay, so let me see what's the correct answer. Here the cumulative distribution function gives the probability of, let us say, anywhere 3. This is probability of a rating given 3 or less than 3, right? But my question is 7 or more than 7. So let me write it on a paper properly so we can understand. So my question is, let us say X is the rating given. So my question is probability of X being greater than or equals to 7. That's what I want. 7 or more than 7. So, but this the information is not readily available here. But we have always less than 7 or less than 6. So we never have more than 7. So what we can do is, we can do something like, what if we know probability of something less and we want to know something more? What do I mean? So let us, we know the sum of all the probabilities is always 1. So if we have all the probabilities 1 and we know probability until 6, so we can say the remaining probability is the probability who gave more than 7. So I can convert this problem into, I say, probability of X less than or equals to 6. I can say this. Why? So probability of X less than or equals to 6, which I already know, which is available here. It's available here from this table. It's 0.28, or we can say 0.3 for as a rounding. So which is equals to 0.3. So the answer is 1 minus 0.3, which is 0.7. So what's the probability that a randomly selected person gave a rating 7 or more is 0.7. there are 70% of the people. So which is also obvious from this data. All we have to do is we have to add all these 3 or 4. If we add all these 4, we get 0.7, you see. So the correct answer is 0.7. So here we have to understand the probability. Another property is the sum of all these values is always 1. The sum is always 1 because it gives the probability, the complete probability. We know the values of probability start from 0 to 1. 0 means not certain, it's not, it's very rare or something like that. 1 is mostly certain or mostly going to happen. So one of these outcomes is going to be coming. So it's going to be 1 or 1, 2, 3, 4, 5, 6, 7, 8 or 8, 9 or 10. The answer is going to be one of them. So the total probability should be equals to 1, right? And the cumulative distribution function, it starts with 0 and it increases to 1. So if you want to answer the other way, so what we do is we find until here and we subtract from the 1 to get the other side, right? So let me plot this x and cumulative distribution function. It is something which increases. Let us see how it looks. Here I like to use this graph because in this case you can use anything, but this one also makes sense. You take any point and all below this we can get the probability, right? Okay. You select what is the probability that someone has given 8 or less, you just put here. So you say is 0.58. So what's the probability someone has given 9 or less? You see 0.78. So from this we get that information. All right. So now let us see. Sorry, where am I? Okay. Now let us see the uniform distribution. So what is uniform distribution? From this slide onwards, we'll try to explore different possible distribution functions. So what the distribution is, we already know, probability mass function. When we talk about discrete random variables, we're talking about the probability mass functions and cumulative distribution functions. The probability mass function, the relation is what we said, different types of distribution. If it follows a certain pattern. For example, here the pattern is it reduced and increased, right? Looks like it reduced and increased. This is a pattern. But there are some certain patterns which are identified and which looks more often you can see in the world. So we recognize those things and we put as a basic models and we want to see them. But remember, the objective is not to understand or take a very deep information into those things. We get a little idea. We don't want to get deeper into that. We don't want to get deeper into the mathematics. The objective is to see there are different distributions available, and we try to understand them. And we see the graphs, and we just make our understanding a little better. We don't have to go in deep into these distributions. Again, I'm repeating, at the last of today's class, I'm going to show you one distribution which is very useful. For that, we try to understand a little bit more in details. Okay, so let us see. The first distribution is called uniformly distributed. Uniform distribution. So what is uniform distribution? So if you have a random variable whose outcomes are equally possible, then you get the uniformly distributed. What does it say? For example, if you have a coin tossing, if you toss once, you get heads. You toss again, you get tails, right? So if you take only one, so you have probability of 50%, 50%. So only once you do, we call it a uniformly distributed. But if you do several times, then we have another, we call binomial theorem. So sorry, binomial distribution. So let us take the uniformly distributed example. Like if you have certain let us say what you call this certain number of let's take the example of a die. You have a die and you throw a die. The probability of getting any one of the sides is equally probable, so it is 1/6. So if you try to make the distribution, you see all are having same. And let me make it example. Let us say uniform. So let us say, so you have a dice example. So let us say x, and you want to say probability mass function. For the die example, so you throw a die, you get 1, 2, 3, 4, 5, 6. So what's the probability of getting 1, 2, 3, 4, 5, 6 is the same. So how much it is? It is 1 divided by 6. Right? Okay, again it's taking some. So it is 1 divided by 6. 1 divided by 6. 0.66. 0.166. Right. If you plot these two, we see that the graph is same. I mean, it's on the same level. It's like a straight line. There is no growing and going down. But here, if you see the previous one for the, what is this example? This is IMBD rating. IMBD, MDB ratings. Here we see it's reducing and then increasing. But here it is the same. So we call this the uniform distribution. And then what we have, we want cumulative distribution function. Right? But in this case, it is same like what we did before. It is applicable for the discrete. So we can do add all these things, and it should start on 0 and it end with 1. Okay, so let's plot this as well. Let's plot this. Here I can plot something like this. So for a uniformly distributed uniform distribution, this will be a straight line growing, and this is a straight line horizontal. Right? For example, I mean the previous example we did from here, when we generate the numbers randomly in Excel, it usually generates uniform, it takes uniform distribution. So if we try to plot this, it looks very similar to this graph. Let us see if it is true or not. We have X here, and we have relative frequency. The relative frequency is probability mass function, right? So let's just draw a plot between these two and see how it looks. It should theoretically look a straight line, but there is a possibility it won't because we are taking very less samples. So let me take this. Okay. So if you see, if it is a uniform distribution, it should be exact straight line. But here it's not exact straight line because we are randomly selecting. When the data goes to infinity, we expect to see a straight line, all these blocks in a straight line, right? But right now it's not exactly straight line. So let us try to generate more data and see if it is really working. Let me see how to do that. Let me try to do that if it is possible. Instead of 2000, I'll put as count, or we can say sum of all. Sum of all of this. You have to log them. Let me log them. I'll log this and I will log this. Right. So let me see if I can generate more random numbers and if I can get more close to the let us see, it is random between, we are selecting between -19 to 19, right? Between -19 to 19. So if you have like some data, so we see it's kind of random already. I mean, it's kind of uniform, but you can't really say it's uniform because it will go down, up, down, up, down, up. So let's generate a lot of data. It's a lot of data, like, let's see if we can generate so much. It's very big. So we generated a very big data. How much it is? 104, or actually 1,048,000 data. So we can see it's getting very close to the uniform distribution because the Excel internally makes its uniform, right? So they generate uniform numbers, uniformly distributed random numbers. So still there is an error. If we generate more and more, it tries to get very close to the uniformly distributed numbers. Okay. So that's the uniform distribution. So now let us see what is binomial distribution. So binomial distribution is an example, like for example, if you see a distribution, let me give an example. You have a bowl of lot of balls, small balls. Each ball is colored differently, and the available colors are, let's say we have only two colors. When we say binomial, we can have only two. One is red, the other one is green. So we have 3 red balls and 10 green balls. So if I take 3 balls from the bowl, I take one ball, I see what is the color, I put the ball again. I take another ball out, I see what is the color, and I put the ball again in the ball. If I repeat it 3 times, what is the probability that I get all the 3 times the red ball? So let us say the question is, we have a bowl of 10 green balls and 3 red balls. If we randomly choose a ball 3 times, what is the probability that it is red all the 3 times? So if you want to know this, if you want to solve this problem, the distribution we are looking for is the binomial distribution. Again, if you don't understand these problems very much in detail, it's not a big problem because we are trying to understand how different distributions work. So if you don't understand exact one simple, one of these techniques I'm using, it is possible that you don't understand, but it's not a problem. The main objective of this is we have to understand there are different types of distributions, there are different types of curves, and how do we try to manipulate, how do we try to use them in our daily use. So one of them we saw is the uniform distribution. So now let us see the binomial distribution. So binomial. In the binomial, what we have is, so we need some information, but let us use the Excel to do that. So X is the random variable and probability mass function, right? It's getting very slow because it's calculating this one all the times. So let me close this. Okay, now it's a little faster. Okay, so Excel is having inbuilt function for calculating the binomial distribution. So we have to see binomial distribution. So here is a binomial distribution here, right? So for this, if I click on this, it will give a help. It makes me understand what can I do with this function. So it is having how many inputs? It's having 3 inputs. 1, 2, 3, actually 4 inputs. The n. Okay, so let me explain what is x so that we can understand what am I doing here. So I have to explain what is the random variable x, right? So x is the number of red balls, number of times the red ball is chosen. So we saw we are taking 3 times. We are taking 3 times out of the what do you call taking, or we are selecting. We are conducting experiment 3 times. Every time you take one ball out, we see what is the color and we put them back, right? So we are doing 3 times. The x represents how many times the red ball came. So what are the possibilities? X can be 0, 1, 2, or 3. So there is no red ball all the 3 times. Some other ball came. Other ball is the green one. So there is only once the red ball has come, or twice, or thrice. These are the only 3 possible things, right? So what are the total number of trials we conducted? Number of trials we conducted, total number of trials are 3. We conducted 3 trials. So what is the probability of success? Now the probability of, what do I mean by success? Success means the one you want is coming. What do you mean we want is the red ball, right? So what's the probability that you get the red ball is called probability of success. So here what is the probability is, so we have a total of 13 balls, 10 plus 3. What is the probability that one of them is red ball is 3 divided by 13, right? So probability of success on each trial. Probability of each trial. So each trial is independent. So if you put the ball back again, it's like a new trial. It's completely random. You don't know what's going to happen. So what's the probability that every time you get it, it is 3 divided by 13, which is equals to, so let's keep 3 divided by 13 and we put it here. So 3 divided by 13. That's the probability of success, right? So now let us try to use this distribution, binomial distribution. S is the success. How many success you are expecting? 0. So for 0, okay, the trials, we are conducting 3 trials. So probability of S, so our probability of success is very less, is 0.2, but anyway we use it. And the last one says, what do you want? You want the cumulative distribution or you want probability mass function? So what I want is right now probability mass function. So I select this as false. So this is the answer. Oops, I have to lock this. Lock this. I have to lock this cell. So I can do this. So what is the probability that none of the times you get the red is very high? It is actually 0.4. What's the probability that you get all the 3 times the red is very less, 1.2 times. So let us say, so probability, so let us say probability that x is number of times the red ball is chosen. X is equals to 3. It's chosen all the 3 times is very, very less. You see, 0.01, 0.012. That's the probability. If you do this, it looks like this. It looks like this, right? I'm going to put a little bigger because if you want to expand the data, for example, instead of 3 trials, if you conduct 10 trials, what happens? So you have more probability. This one is so until 10, it makes sense. After 10, it doesn't make any sense because if you are conducting only 10 trials, why do you ask for it? So these are invalid questions in this context. So if you are conducting 10 trials, and what's the probability that you get 3 of them being red is at least 3 red size, 0.23 or 23%. So if you pull 10 times and all the 10 times you want it to be red, the probability is very, very less. It is not impossible. It is not, probability is not 0, but very close to 0. If you see, it is 4.2 times 10 to the power of minus 7. It's like very close to 0. It's almost impossible that you can do it. Okay. So that's the probability mass function. If you see probability cumulative distribution function, it looks, the formula is the same. We use the same formula. But here, instead of false, we say true. And here it gives this one. So let's plot this. And let's plot using the line kind of thing like this. So we know it starts from 0, it goes to 1, right? That's the probable binomial distribution. Let's see an example. Say a coin is tossed 10 times. What is the probability of getting exactly 3 heads? So we have this, we use the same page. Let's use this. So we are tossing how many times? Let me see. So we are tossing 10 times. So we are tossing 10 times. Okay. What's the exact 3 heads? Okay. So but the probability of success here is 50-50. So there is 50% chance for heads, 50% chance for tails. So we use 50-50. Here 50-50. The probability mass function looks like this, and the probability cumulative distribution function looks like this. So let us say 5. No, say exactly 3 is right. So the answer is 0.117. So it is 11.7% of the times you have chance that exactly 3 times it's head, and remaining all will be tails. For example, if I ask you a question, what is the probability that it falls 6 or less than 6 heads? So what we can go is to go to the cumulative and we say 6, which is 0.82. So 82% of the times it will have 6 times heads or less than 6 times heads, right? So that we can understand from this graph. So next question is Poisson's distribution. Poisson's distribution tries to answer the question of let us see an example of how many times it happens. When we have some question related to that, we answer using Poisson's. Well, let me explain again what do I mean. So let us say you are in a bus stop, and the city you are talking about is a 24-hour city, and it works the whole day, and the buses pass there randomly. They don't have any exact timings. They randomly pass around. So I'm creating a universe with this kind of this type of information, right? They're randomly passing, the buses are randomly passing, and you are standing at a bus stop and you want to know how many times a bus is passing in 1 hour. And the information you already have is, at an average, the buses pass in 1 hour, 10 buses pass. So here is the bus stop. So here is a bus stop, you are standing. We have a road in front of it. We know, and on an average, there are 10 buses passing. There are 10 buses passing on an average per hour. So 10 buses per hour. And you are standing here for 1 hour. Standing here for 1 hour. And you want to know what is the probability that there are at least 2 buses passing. Or what is the probability that there are 12 buses passing in the hour you are standing there. So you already know on an average 10 buses will pass. But in the hour that you are standing, what is the probability that there are 5 buses passing, 2 buses passing, 3 buses passing? This question is answered through the Poisson's distribution. So how does the Poisson distribution works? So let's open one sheet and let's make Poisson's distribution. Poisson's distribution. Here we need the information we need is the mean. We want to know what is the mean of the distribution. So what we have is x, and what we want to know is probability mass function, cumulative distribution function. So let us say x is 0 buses are passing. Let us say mean is 10, right? 10 buses pass every hour. What are the possible values? There are no buses passing. There is only one bus passing, 2, 3, like that. You can have any discrete number. The number can be more. Even you are very lucky and there are like 30 buses passed. What's the probability that happens? So how do we calculate this? Is using, let's use the inbuilt functionality of the what you call the Excel. It has Poisson's distribution. What we need is the x. It needs 2 variables. One is x, another is mean, and it wants to know what you want, your cumulative or probability mass function. So we want probability mass function. So we say it is false. And for the cumulative, we want the cumulative one, right? So we take the for the cumulative, we say it is true. Okay. So let us fill the whole table. But before I have to lock this, the B1 should be locked. Here again, I have to lock the B1. Now let me fill the whole table. Okay. So what's the probability that exactly 10 number of buses are passing is 12.5. So 12.5% of the time in an hour, exactly 10 buses will pass. So let us see with these numbers, it makes sense, but it's not so easy to understand. So if I put it on a plot, it makes me more easy to follow. Let me put it. I can draw like this, but I don't enjoy using this because it makes me feel like there is something between these two numbers, which actually doesn't make really any sense. So let me use this like this. So if you see this is a probability mass function. So it says if there are 10 buses passing at any randomly selected 1 hour, if you go stand there, what is the probability that exactly 7 number of buses passing is 9%, because it's 0.09, which is 9%. But still there is no there is possibility for any number of buses to pass. Even 30 buses can pass, but with very little probability. So it's 1.711 times 10 to the power of minus 7. It's very little probability, right? So it's more than million time. It takes very big numbers to do that. Okay. So if you see this probability distribution, you can notice that it's a little skewed towards the right. What do I mean by skewed? If it will be more exaggerated if I put a number closer to the 0. If I put a number close to 0, let us say 4. You see it rises quick but falls very slow. We call it the skewed towards the right. So if it's a 12, it rises and falls a little slowly towards the right. Okay. Yeah. So this is the Poisson's distribution. Okay. The example. Okay, we have an example here. We say we are expecting 5 metroid. Okay, let's pronounce it as a comment. Let's say 5 comments. We are expecting 5 comments to see per hour. So what's the probability that see at least 2 in a 1 hour? So it's a really interesting question. So the question says you are standing, let us say you are standing on some open sky. So you are standing there, here you are standing and looking at the sky, and you see the meteoroids or the comets are falling, and you are given the data that at least on an average 5 comets fall every 1 hour, and every 1 hour 5 comets fall. That's the average. For example, you are standing there for 1 hour, so you are here for 1 hour. The question is, what is the probability that we can see at least 2 meteoroids? At least 2 means 2 or less than 2. It's a very interesting question because for 2 reasons. One, it is because it's not available directly. You can calculate. Another one is because in Poisson's there is no upper limit. Means you can't exactly say what is the probability if you keep continuing from this side direction. Like for example, if you say even for 40, there is still probability. Even if there is no possibility like you stop here and you add all these things and gives the probability. You have to add infinite numbers to get at least 2, means 2 or more than 2. So you have to add all these infinite numbers, right? Which is something we can't do it. For that, we have to use another technique. So let me see the technique. So the question says the mean is at 5. The mean is 5, so I change the mean to 5. And this is the Poisson's distribution. So we have it like this. So we have 2 or more than 2, because that's what it says. At least 2 means 2 or more than 2. So what's the probability we're expecting is 0.02. Sorry, this is average. The sum is this one, 0.9595. So the probability is 0.95, but it's not accurate. It's accurate to our human eyes, but if you see, it's 10 to the power of minus 23, and there is an error 10 to the power of minus 23. If you want exact value, what you can do is you can change the question a little bit and you get exact answer. What do I mean? Let me change it. The same like what we did before, but let me explain here. So the question says, first let's explain what is x. X is number of comments you see in 1 hour. So what we want is probability that x is greater than or equals to 2. I want to know it. But we saw it's not very easy, it's not very direct. But what we can do is probability of x less than 2, or you can say greater than or equals to 1. So we know this, we can calculate this. So what we can do, this is equals to 1 minus this one. So total probability minus probability that you see 1 or less than 1. So if you remove that, then we get the probability that 2 or more than 2. So we already know 1 is 1, and the probability of getting x is equals to 1 or less than 1 is the cumulative distribution function, which we can calculate here, which is 0.04, 0.0404, 0.0404. So if you do this, 404 is 0.9596, right? It's 0.9596. So the probability is 0.9596, which we already saw from this adding, which is 0.9596 approximately. So we can add all these numbers, or we just subtract 1 minus this number, which makes more sense and more easy, right? Okay. So now let's see the probability density function. Here it is very important to understand what is probability density function. Before going to this in detail, let me ask you a question. So let us say you have a dart, right? You know what is a dart? A dart game which we play. Some people play in the clubs. So you have a round target. There are several circles in between. Let us not draw all the circles. You have a dart like this, and you have a pin in your hand. I'm not drawing it properly. Let me show you the picture so you understand. So this is what I'm talking about. This is a dart, and we have a pin, and we throw a pin, and it falls somewhere on the dart. Let us say we are throwing a dart pin randomly, and it falls somewhere on the dart all the times. So randomly, it doesn't mean that you are targeting something. What I mean is you are not targeting to the center. You are randomly throwing it, and you know it will fall on the dart, somewhere on the dart. There is an equal chance for this dart to fall anywhere on this dart, on this base. So my question is, what is the probability that it falls exactly at the center? Exactly at the center point. Exactly at the center point. So I'll post a poll. You answer it. The question is, if you throw a dart and it's random, my question is, what is the probability that it exactly lands at the center of the dart, this base? Let me ask a poll. Okay. What is the probability that the dart lands on center of the base? I call it base. Maybe you can say the, I don't know what to call this exactly, the table. Let me see, table or base. Or, so the answers can be 0. Yeah, the question is ready. What is the probability that the dart lands on center of the base? If the question is not clear, you can ask me again, I will explain. Please raise your hands if the question is not clear. Yeah. Okay. So Edgar, so I think the question is not clear, right? So let me explain again. Let me show you the screen. Share my screen. Okay, so let me explain question from the beginning. So we have this dart table or base, we call this circular one. You throw the dart, I call it the pin or dart, you throw it and it goes and hits somewhere on this circular table. So my question is, what is the probability that it hits exactly at the center of the circle? Dart hits exactly at the center. What's the probability? You don't have to know it. If you can just give some guesswork. You don't have to like do mathematical calculation. You can just guess it and tell me. Yeah. We have a poll. You can answer the poll. Just look into the poll and answer it. Are you able to see the poll? Poll is not available for you. Or you have to click here in the bottom and it says poll. Let me stop it and make again. What is the probability of dart landing exactly the center of the circle if you throw a dart .0, 0.1, 0.5, 0.9. Okay. Right. Is it available now? Yeah. So it's 0.1, 0.5. It's a guesswork. You don't have to do any calculations. You just guess something and you can just put it. You don't have to be like defending yourself. You can just have to. I want to know what do you think about it. Okay, now let us see the results. So the responses, one person says 0, 4 says 0.1, 1 says 0.5, 1 say 5, one person say it's 1. Okay, so I want to know the person who says 0, why do you think it is 0? The person who said the answer is 0, can you please explain why do you think it is 0? I'm asking it because that is the correct answer. So I want to know what is your way of thinking? Why did you think that that's the correct answer? What made you think so? So what was the thinking process which made you think that the answer is 0? That's actually correct. So I want to know why is it? You want to share your thoughts with us? Okay, it was a guesswork. Okay, that was a good guesswork. Okay, let me explain why. So it is area, right? So it's area, a dot is going and landing in some point. So I'm using this because the dot tip is kind of zero dimensions. It's like a point. A point doesn't take any dimension, it doesn't occupy any space. And this is an area. You have an area. So how many points you can put on an area? So this dot can land here, 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 anywhere. It can land anywhere. So if you take any point, it doesn't have dimensions. But how many points you have in a given area? We have infinite number of points. So if you see calculate, how do we calculate the probability? We calculate the for example, outcome divided by the total sample size, right? So the outcome, for example, in tossing, we say heads or tails divided by the total possibilities, which is 2, head and tails 2. So it is 1 divided by 2, which is 0.5. So but here you have 1 point. You selected 1 point. And how many points you have? You have infinite points. So in denominator you have infinite. And numerator you have 1, let us say. So 1 divided by infinity is 0. So the probability of falling at any selected points is 0. But we know it falls somewhere on this. So it's kind of tricky way of thinking. So it falls somewhere. We know it, but the chances of falling at any point is infinite. Sorry, it's 0. You can't say it will fall here. It's not possible. It's very, very, very unlikely to fall any pinpoint. So I'm talking in the dimensions very, very small size, right? So but the probability changes. For example, so what we say is we don't use the pinpoint anymore. What we use is the regions. So if you have a circle, what's the probability that it falls in this region is something we can calculate. For example, let's say the big circle is having an area of 10 and the small circle is having area of 1. So what's the probability that the dot falls in the region of the small circle is 1 divided by 10, which is 0.1. That's the probability. So when the x or the random variable is continuous, you can't talk about probability at each point. It makes no sense. You have to talk probability in a region. When probability is when the variable and the random variable is continuous. For example, if I ask what is the height of a randomly selected person on a street is exactly 6 feet, the answer is 0. There is no human with exactly 6 feet. It will be little more than 6 feet or little less than 6 feet. So what I have to say is a randomly selected person on a street, what is the probability that his height is 5.9 to 6.1? Then you can say there are 10% of the humans or 10% of the population on this street are having this height, right? So you exactly pinpoint anything, it's not possible. It's not possible mathematically when you are dealing with random numbers of what we call this continuous random numbers, right? Okay. So we deal with the called probability density function. What is probability density function? So we can see this through some examples like uniform distribution. But I want you to do this part of uniform distribution. You look by yourselves how it looks. I want to show you with some other ones, like for example, the exponential distribution. So what is the exponential distribution says? Let me show you here. Then exponential distribution. Here in Excel, it generates automatically. I have to use this formula and it generates. So anyway, what does it says is probability density function. Density means how dense it is. So it is very dense at 0. It's slowly reducing. So if you see, this doesn't have anything to do with the value of probability directly. What do I mean? We know the probability, the value of probability is always between 0 to 1. But here if you see the value is going to 4. It doesn't mean that probability is 4. It means it is very dense. It is 4 times more dense than this point. Because the probability is 4 here, it is 1. It's more dense there. So you can expect more values closer to 0, right? Okay, so how do we calculate probability? We calculate in some region. So what we can always calculate probability from 0 to 0.5. So what's the probability that it is between 0 and 0.5? So probability density function doesn't give answer directly. What you have to find is the region or the area or the painted area. If you paint all this below this or the area under this curve, it gives us. In the terms of calculus, we say is the integration. Integration from 0 to 0.5 gives us. Okay, for this, we have the cumulative distribution function. The CDF gives us the same result. What does it give is the integration of the PDF. So what we are seeing here is, for example, you want to see 0 to 5. What is the probability that the value takes between 0 and 0.5 is you take 0.5 and this is the value. For example, 0.5 is 0.8. So 0.8 is the probability that it is having a value 0.5 or less than 0.5. We know it starts from 0 to 0.5, right? So we have to understand this. The probability density function gives us the probability how dense it is at certain values. It doesn't give the value of probability directly. To calculate the probability, we have to do integration. We have to do integration or we use the cumulative distribution function, right? Okay. So this is exponential distribution. And there is another one called, we said this one is the most important thing we are going to see at the last. This is a normal distribution. So this one is very important. We dig a little deeper into this. In this class, we see just superficially, but in the next sessions, we try to understand more in detail and try to use this, right? So for a normal distribution, we need two information. One is the mu, which is the expected value, or we can say the average value. And then the sigma. Sigma is the standard deviation. We have these two information. We can calculate the normal normal distribution. For example, if you have a mean 5 and the variance is 10, so the curve looks like this. It's only half. So let me put the mean is equals to 2. So it will look small. So it increases, it decreases. Let me put variance a little bit less. So it's like a bell shape. It increases and decreases. We try to understand this more in detail in the next classes. And the cumulative distribution function is always increases and it's kind of a S shape, the shape of a alphabet S, right? So again, this 0.4 doesn't represent the probability. It represents it's more dense at this, right? So, and then we have another one called standardization of the normal distribution. What is standardization of normal distribution? It's the same normal distribution, but the mean is 0 and the variance is 1. Once we have this, we call it the normal distribution. So why do we use the standardization is because to use certain tables. There are some tables called Z transform tables. So Z table. So it's not a Z transform, it's Z score table. So this table gives the area from negative infinity until the Z. What is the Z? The Z is normalized value. Oh, sorry, it's not normalized, it's standardized. Standardized is x minus mean divided by the standard deviation. So if you do this, what happens is you take any curve, any normal distribution, it converts into the Z, this one. So you can interchange your values. So all these things we'll see in the next class. Here I'm just giving like an introduction so that you can understand what we are going to deal with in the next session. So that's all today for today. The most important thing is to understand the normal distribution and how to do this in the next sessions. So if you have any doubts, you can ask me. This is all for today. Okay, so if you don't have any doubts, we can close for today. I hope it is useful for you. Thank you very much. Thank you, Valeria. Next session. If you have any doubts, send me an email. Let's make a time where we can sit together and solve all the problems. All right. So send me an email and let's find a time and we make another conference and we solve all your problems you have with the assignment and all. Right. Okay. So have a nice week and see you.